First, I want to thank the organizers for inviting me to share some of my work here. And today, I'll be talking about high-temperature thermodynamics in the context of the virial equation of state. And this is work I've done with my collaborators at Washington State University, and this is work funded by the NSF. So the outline of my talk, first I'll motivate why the cluster and high-temperature virial equation of state is interesting and where it's useful. And to do that, I'll introduce the method that we use and then give a quick textbook warm-up into the virial equation of state. And then once we're all on the same page, I'll get into the more interesting things of a two-component Fermi gas, equal mass, unequal mass, in the strongly interacting limit and weak interacting limit. And then hopefully if I have time, some new work into the dipole quantum gases in the same context. So this is not a new concept. The cluster expansion really comes from a very physical picture that we have. So we know in the high temperature limit we have the ideal gas. And so in a many-body snapshot, you see the particles spend a lot of time far apart. They don't really communicate with each other. But then as we lower the temperature, the quantum nature of the particles becomes important. And so what we have, in a sense, you can think of they spend time far apart. And now the first order correction to this comes from two-body effects, or two-body clusters, in which if the particles are identical, you have to consider either interspecies interactions or the quantum statistics of the particles. Or if they're distinguishable, you have to think about the interspecies interactions. And then the next order correction would be three-body clusters, where you have to consider both the interactions as well as the particle statistics. So in the work that we do to compare best with the experiment, this is a high-temperature expansion, but we're not going to go to so high temperature that we have to consider higher partial waves. So we're going to work in this kind of magical regime from about the Fermi temperature to just where we can consider only S-wave interactions. Another way you can think about this, as I mentioned earlier, is the de Broglie wavelength getting larger and larger, and the parameter here, which is the de Broglie wavelength times the density. So how we look at this is in terms of the grand canonical ensemble. So here is where we're going to start our textbook introduction. So here I have a single component gas, and how we describe this is minus k volts from T times the log of the trace, the exponential of the Hamiltonian. And we also are considering any number of particles in this picture, so we have to have the chemical potential. And the first thing that we do is we can actually rewrite this in terms of the canonical partition functions and the fugacities, which are related the exponential of chemical potential, or k volts from T. And what we see is that you might think, okay, this is too difficult, we have to solve every n-body problem. But in the high temperature limit, the fugacity becomes a small parameter. And so what this allows us to do is a Taylor expansion around the small parameter, and then we regroup our terms into these expansion coefficients. So we've gotten rid of this natural log here. So this is a very nice form, because then it allows us to possibly truncate this expansion at second, third, so on order, and try and actually accurately describe the high temperature limit of these gases. The difficulty now is not in solving the large n-body problem, but now it's reduced to solving the small n-body problem. But we still have to have, at least in this picture, all of the energy, a large portion of the energy spectrum to calculate the virial coefficients. And they are actually polynomials of these canonical partition functions. And just to maybe get an idea, if we're talking in this case about a single component gas and say non-interacting, all we're considering here are quantum statistics that go into these virial coefficients. So we might think, let's say if we have a single component gas of bosons, non-interacting, we know we have polypressure, which will push everything out. And so if this is in terms of energy, negative energy, if we want to have a slightly repulsive gas, and then we might consider if we truncated this at second order, the virial coefficient should be negative, or V2 should be negative. So we'll actually see that later. Continuing with our textbook example, let's just take a look at three problems we might find in our favorite statistical mechanics textbook, Macquarie, what have you. So what I have drawn here schematically are three potentials: the potential periodic boundary conditions with a unit cell length L, a harmonic oscillator with trapping frequency omega, or an absolute value potential with a slope dictated by alpha. We can actually characterize these systems based on a non-universal parameter, which is the ratio of the energy scale of the system with respect to the thermal energy scale. And already we see something interesting in looking at these different systems. In particular, we see that in some cases the mass plays a role, while in this harmonic oscillator case, the mass does not play a role in the energy scale. And we'll actually see how this impacts later studies. And then, following the procedure of calculating just the first canonical partition function, we sum up all of the states. We can either do this exactly analytically or solve some transcendental equation to get roots. And since all the physics is contained in the statistics, which is a one particle effect or a one body effect, we can really think of this all in terms of Q1. And in the high temperature limit, I'll note that they have different forms, but they're all related as functions of this non-universal parameter in high temperature limit. So as I mentioned a few slides ago, what we should expect for a single component gas of non-interacting fermions. And checking the back of our textbook to make sure we did all the math right, we see that, so we haven't broken physics. And what I have plotted here is B2 as a function of this non-universal parameter, so I can plot all these different systems on the same graph. And what we see is they have very different behaviors if we go towards low temperature, because you can think of this as an inverse temperature scale. So low T is over here, high T is over here. And what we see is that as they approach the high temperature limit, they always approach constant. So then you might ask, well, how are these systems even related? They look nothing similar except they all give the correct sign at second order. Well, what we see is, for example, in the harmonic oscillator case, you see that it always approaches a constant in the high temperature limit, so this is a Taylor expansion in this non-universal parameter. And then there's some correction, linear, quadratic, what have you. In the harmonic oscillator case, it's quadratic. And then how these systems are related, we can relate them using the local density approximation, where what we have is a canonical partition grand canonical partition function density. And what we can do is we can integrate this over all space, where the density really changes due to our confining potential. So we have a global chemical potential modified by the underlying the trapping potential. This in turn modifies the fugacity and can integrate over all space. And again, this is a 1D example. And what we see in the high temperature limit, the universal high temperature part of these coefficients is related to the homogeneous with just some interesting scaling. So in effect, we understand the non-interacting system. So again, this is textbook, hopefully we're all on the same page. So we want to introduce interactions. And so the clusters that we are going to study is the 2, 3, and 4 body clusters for the equal mass 2-component Fermi gas with only S-wave interactions. And if we wanted to actually look at the unequal mass system, we're going to stop at third order. And then if we wanted to also look at a new type of interaction for us, a dipole interaction, we're actually only going to go to second order. But in this case, we can look at either weakly interacting fermionic dipoles or bosonic dipoles, in which we have to not just consider one partial wave, but many couplings to other partial waves. So then, how we actually do this, our approach is to look at these few-body systems in a harmonic trap. And what we're going to do is calculate a large portion of the spectrum, and hopefully very accurately. And then once we build up the low temperature tail of the virial coefficients, we're going to try and extrapolate to the high temperature limit, which is more interesting to experimentalists. And then hopefully use the local density approximation to calculate the homogeneous values. And also, at least for starters, we're going to consider spherical trapping. So all particles yield the same trapping frequency. And we can look at different masses, which I'll get to later, but for now we're going to consider equal masses. The technique we actually use, if we can do things analytically, say unitarity in some cases, or semi-analytically, we'll use a zero-range pseudo-potential whose strength is characterized by scattering length. Or if we can use a basis set expansion using the stochastic variational approach. And where we have a finite range interaction, but we extrapolate to infinite basis, as well as extrapolate to zero range. So some questions I hopefully can answer by the end of this talk is, can we calculate the fourth order? The second and third are known semi-analytically for a while now. And then hopefully I can also answer what role the mass plays in the system. So complicating our textbook example, since now we have a two-component Fermi gas, we now have to consider a two-component grand canonical potential. So it's not so complicated from the single component case. We have one fugacity per component. And in the high temperature dilute gas limit, we can Taylor expand this and think about it in terms of two non-interacting single components together with some kind of correction due to interactions. Now, I'm going to focus at unitarity for a good portion of this talk. And why this is interesting is the divergent S-wave scattering length leaves the trap length as the only non-universal parameter. So everything that we've looked at in our textbooks for the non-interacting system is going to come back to us in the unitary limit. And so it's going to be interesting that our intuition that we built in the non-interacting system can be applied in the unitary limit. So for those who may not be familiar with what the virial coefficients look like, I've plotted them here as second order and third order as a function of this non-universal parameter for a spherically symmetric trap, harmonic oscillator trap. And again, this is the inverse temperature scale. And what we see at second order, the value is positive. So we can make sense of this. We have an attractive system. And so if we truncate it at second order, we should expect a positive virial coefficient, because that implies an attractive gas. And then at third order, we see that the scale going to higher order at high temperature is less. And this is actually the trend that we see for all the virial coefficients. They get smaller and smaller in magnitude at the high temperature limit. And nothing exciting really is happening at second and third order. These are known, as I mentioned, semi-analytically. And in the high temperature limit, where we can connect with the experiment, these are known to whatever order vacuum. So now the question is, what if we move away from unitarity? I'll explore this question by looking at second order. So what I have plotted here is the second order virial coefficient as a function of the non-universal parameter. But what I've done is I've gone from unitarity, which is this dash dotted curve, and then lowered the interaction strength. And so what we see is actually the second order virial coefficient is decreasing. And this makes sense because if I start to turn off interactions, the corrections due to interaction should be diminishing. But what's interesting, we see in the high temperature limit appears, no matter what the interaction strength, it always goes back to this universal value of 1.5. And this kind of puzzled us for a while, but I think we have a pretty good understanding of it now. You can actually examine the unitarity limit using the perturbative approach. What I have plotted here is the energy, the two-body energy, as a function of the inverse scattering length. And what I actually have plotted here is the n equals 1, 100, and 1,000 energy level. And what you see is that as a function of the inverse scattering length, the energy levels are actually flattening out as we go to higher and higher energy. And why this is important is in the high temperature limit, we're including more and more states in this sum of states. And so what we see is that as this flattens out in a perturbative approach, which is the linear approximation to the energies, we see that the perturbative approach is going to be more and more valid over a larger inverse scattering length range. And you can actually calculate an exact expression in the high temperature limit, which is valid in the high temperature limit. And you see that it varies as linearly with the inverse scattering length. But what's interesting is there's this first term here, which is independent of the scattering length. And at the high temperature limit, this is equal to 1/2. So we can actually, using the perturbative approach, calculate the exact deviations from the high temperature unitary limit. Now, this is all done in a spherically symmetric trap. And we know that experiment doesn't usually use a spherically symmetric trap. So you might be thinking, okay, this is all well and good, but what happens if we have, say, a cylindrical aspect with a cylindrical trap? So let's examine this question at third order. So what I have plotted here is the third order virial coefficient as a function of the universal parameter, and in this case it's the frequency in the z direction. The black curve is the one that I've shown previously for the spherically symmetric trap. And then we have cigar-shaped aspect ratios in these red and blue curves. And the amazing thing is that in the high temperature limit, the virial coefficient is independent of aspect ratio. So what this means is in experiment, it doesn't matter if you have a cylindrical trap, pancake, spherical, what have you. So long as you're in this universal, in terms of temperature regime, you should get the same results. And I'm not saying that you can go all the way to a purely 2D system. I mean, what this is saying is that you can really think about this in terms of thermodynamically, you're accessing all of the different energy levels, including the ones in the tight or weak confinement axes. Another interesting thing that we see is that if you actually plot this using a nice choice frequency where we take the average trap frequency, all of these curves collapse to the same universal curve. So again, showing that this is really the physics is independent of the trap aspect ratio. This also works surprisingly well away from unitarity, but I don't have a figure to show that here. So now that we understand that we can actually go back to the spherically symmetric trapping potential and still get all the same physics in the high temperature limit, let's then return to the strongly interacting unitary system and try to do this at the fourth order. So fourth order is a bit tricky because again, we're solving the four-body problem to get this, and it's not so simple. And we need to calculate a large portion of the energy spectrum fairly accurately. And since this works for the second and third order, we suspect why not for the fourth. So again, to reiterate our method, we calculate a large portion of the low energy spectrum, and we have truncated the number of states we include, and then we try and extrapolate to the high temperature limit. And I'm plotting the third order here just to show that it can be done with actually very good accuracy. In this case, since we have a semi-analytical problem, we can do this with any accuracy. So our assumptions going into these fits, at least our initial assumptions, was that the virial coefficients as a function of the non-universal parameter change monotonically, at least for the harmonic system and harmonic trap. And also they happen to be even functions, and you can show this in the non-interacting limit. You can actually show exactly they're even functions. So they should be in the unitary limit. And so we apply this to the fourth order, which I have plotted here, fourth order virial coefficient as a function of the non-universal parameter for three different truncations of the number of states we include. And it doesn't look so bad. The only problem is we can't go to nearly as high temperatures because it's much harder to calculate the energy spectrum. But we try this anyway, and we extrapolate to a negative value. And if you're maybe not aware, experiment takes the cake, and we don't agree with two different independent measurements of the experimental value, which is small and positive. So what this tells us, not so much that the fourth order doesn't work, but that it must change sign. And so basically we're limited by the number of states that we can calculate, so our assumptions may not all be true. For example, changing monotonically, we must throw that one out. And maybe if we could include more states, we might actually see a turnaround. But we did not pursue that. So it's a bit disappointing. This method is extremely challenging because it involves solving for a large portion of the energy spectrum, and already at fourth order, we see that we can't accomplish this with the number of states we've already calculated, which is the order of hundreds of states. So let's see what happens when we actually change the masses now. So at a few body level, interest in physics already happens when we have unequal mass systems. For example, you might have an FMOF trimer form when you have two heavy and one light particle in a two-component Fermi gas. Although the two light and one heavy is nothing interesting. But what we see when we talk about unequal masses, at the two-body level, nothing actually changes if we still calculate this in terms of the reduced mass. So that coefficient won't change. But we might start to expect something interesting to happen at the three-body level, which should impact the third-order coefficient. At the many-body level, what happens when we change the masses between the two species, we now have two different Fermi surfaces. And we already maybe can get some intuition of what might happen, because we know if we start with an equal mass system of a two-component Fermi gas, if we change the relative number of spin-up and spin-down particles, we know that we can actually get interesting configurations where, say, the core is a superfluid core with a normal gas with the excess component. So maybe we should expect to see something like this when we change the Fermi surfaces by changing the mass. So I'm not showing the second order virial coefficient here because, as I said, nothing changes. So I'm starting with the third order component. And what I have plotted here as a function of the, in a spherical trap, the non-universal parameter for mass ratios. And this is kind of nice to see that the high temperature limit is changing, which is interesting. But we already see that also these are non-monotonic functions of the non-universal parameter. So it's kind of nice that even though the fourth order equal mass system kind of failed on us in our approach, we see at least more evidence why we can't make that assumption of monotonically changing functions. What I have plotted here is just the universal limit of the virial coefficients in the high temperature limit as a function of the mass ratio, where from 1 to large numbers, this is 2 heavy and 1 light, and over here is the universal limit for 2 light and 1 heavy, just plotted on the same figure. So one of the things also in this work when we introduce unequal masses is there is also a lot of interesting physics that's happening at mass ratios around 8 to 13.6, where the FMOF trimer comes in at unitarity. But I'm ignoring that. I'm considering only universal physics through all mass ratios considered. And the other thing that might have caught your eye is how the virial coefficient is changing as a function of mass ratio. It's increasing and actually changes sign itself at about a mass ratio of 3 or so. And we can actually understand this because the virial coefficients of the few-body system, they contain the physics of the few-body systems. What I mean by that is let's go back to the second order virial coefficient. And in this case, I'm plotting it as 1 over KFA. And we know in the two-body system, we will pull in a bound state when the scattering length is positive. And whenever we have a bound state, which is a negative energy state, it comes into the Gibbs factor in such a way that you get a very large contribution to the virial coefficient sum. And so that's why we see this positive deviation, or positive growth of the virial coefficient as a function of these inverse scattering movements. And that's also something that we see here if we turn our magic knob, not accessible to experimentalists, to change our mass ratio. And what we see is a positive growth of the virial coefficient, which indicates the onset of a bound state. In this case, it's the trimer bound states that occur in the system. So this is maybe a little bit more technical, But what about the thermodynamics? I'm just calculating numbers. Maybe a very difficult, convoluted way to calculate numbers, but how do these numbers actually go into the thermodynamics? And once they go into the grand canonical potential, we can just, using textbook equations, we can calculate certain thermodynamic quantities. In this case, I'm actually, for the unequal mass system, I'm plotting the free energy per particle as a function of the polarization, which on the far right, I have a majority of heavy particles, and on the left, I have a majority of light particles. What's interesting is, if I were to truncate this sum at second order, truncate the series at second order, as I mentioned, at the second order, nothing changes when I change the mass. So actually, I would only see a completely symmetric shape to the free energy. So what this indicates, we're the minimum of the free energy, that's the equilibrium position. And so we really have to go to third order, which is what these curves are, the third order virial equation of state with to calculate the free energy with ever increasing mass ratio. So one of the interesting things that we see is a shift of the minimum of the free energy as the mass ratio increases towards a majority of heavy particles. So what this indicates is if we have a mass imbalancing system, that the system would prefer to minimize its energy by actually having more heavy particles than light. So we might speculate that if we were to start actually with a spin balanced gas of heavy and light particles, we actually start out of equilibrium. And so maybe the system might phase separate like we saw with the equal mass system with a spin imbalance. So how does this translate then into the homogeneous system? We can apply the local density approximation to calculate the virial coefficients of the homogeneous system. And then what I have plotted here is the free energy per particle as a function of the polarization. And the first thing to notice is that there's a very large shift towards a majority of heavy particles, even for the non-interacting system, which is shown as the dotted lines. And this can actually be very simply understood by an energy argument, where if you have the kinetic energy h bar squared over 2m, if you have a larger mass, then you have a smaller kinetic energy. So the system wants to have a majority of heavy particles to lower its energy. But we see as we turn on interactions and we include up to the third order, which is the solid blue lines, the system is slightly pushed back towards the more balanced system. So it really wants to have an imbalance. So in this case, 2 heavy and 1 light is really almost the best way to minimize the energy by forming these triangles. So maybe I've given you a nice picture of thermodynamics in the two-component Fermi gas, is also with unequal masses. But also, I would also now move into what happens if we include dipole-dipole interactions. So the dipole-dipole interaction is interesting because now we have an anisotropic interaction. It's very long range. But a lingering question for us is this actually behavior observable at high temperature? And so the method that we use in terms of adding up a whole bunch of energies is still the method we're going to use. But now we have to consider all the allowed channels, not just the X-wave interactions for the case of either distinguishable or two identical bosons. And so what we're going to do is a more simplified picture. We're going to model all the short-range physics by a hard wall. And then we're going to calculate the second order virial coefficient for a spherically symmetric trap. And we're going to have a perturbative limit where we have very weak dipoles. The other thing we have to consider is also that the dipole interaction introduces a new length scale on top of the trap length. So the dipole length, which I indicate by capital D, is related to the dipole moment. And this in turn also relates to a new energy scale, the dipole energy scale. And to simplify this talk, I'm actually going to stick with talking about fermions. So we're going to have two identical fermions that are aligned, dipoles are aligned. And so we're only going to be considering the odd angular momentum channels. So as I mentioned, we're going to use the same technique as before. So in this case, we're going to use a nice transcendental equation But what's interesting about this equation is it actually requires knowledge of all the generalized scattering lengths. But we can actually get those by solving a multi-channel problem and extracting the scattering length from the K matrix from this calculation. So what I have shown here on the right is for m equals 0, because we can actually solve independently for every projection quantum number. This first plot here is the generalized scattering length A11 as a function of the dipole energy. And what we see is we can actually see dramatic behavior depending on the ratio of the dipole length to the short-range physics of the hard wall. If we had chosen a different value here, this would actually approach the Born approximation limit, which is about -0.4. And so if we look at the other scattering lengths, they're getting smaller in magnitude as we go up to larger channels. But what is interesting to see is that the Born approximation are these flat plateaus here. And if we actually translate this to a weak dipole system, we're only considered in energies from about here onwards. So we can actually use the Born approximation to work for calculating the energies. And we'll even choose values here where we can maybe adjust the value of this smallest channel scattering quantity. So to be quick, the conclusion from this work, which was a very challenging work to calculate a number, it's very disappointingly difficult to observe the dipole of physics, especially away from resonance where the Born approximation is valid. So what I have plotted here is a second-order virial coefficient as a function of the non-universal parameter, where I consider all scattering lengths in the Born approximation. And just look at that. Oh man, that's that. It's all orders of magnitude smaller than we saw in these other two-component Fermi gas systems. But there's hope. So what if we actually have the ability to tune the scattering length, say the A11 generalized scattering length, by, say, going towards a quasi-bound state in the system? Well, if we have control over even just one of the scattering lengths, we could actually modify the behavior of the virial coefficient. And in this case, we see we can even flip the sign and also increase it by about an order of magnitude. So maybe experimentally, there's actually an interesting amount of control we can have in looking at the high temperature physics. This can actually also be understood why this is such a disappointingly small number. Is in the Born approximation, you can show very nicely that the lowest order term is linear, but in the Born approximation, all of the coefficients, all the scattering lengths cancel. So really, the linear dependence goes away, and we have a quadratic dependence on the dipole length. And because I'm in the perturbative limit, if the dipole length is, say, 0.1, I mean, this is just very much suppressed. But again, if we have control over one of these values, we actually recover the linear dependence on the dipole length, and we might actually be able to see some more interesting physics in the high temperature limit. So to summarize, hopefully I've given you a nice picture of how we can actually translate few body physics to many body physics using the virial equation of state. And there's a lot of open questions. For example, can we stop at second order? I put that one up there kind of in caution though, because short answer is probably no. And then what role do the higher orders play? I've actually truncated all this work either at second or third or fourth order, and we haven't calculated the five-body system energy spectrum, so we don't know what happens if we include the next orders in these expansions. And then the other thing is we always worked in a spherically symmetric trap. So do we know what happens if we actually allow the species to have their own trapping frequencies, which this would couple the center of mass and relative degrees of motion, which makes the numerical work a bit more challenging. And then quick with the dipole effect. Disappointingly small number, but again, we were in a spherically symmetric trap. Maybe we can actually show by going to different aspect ratios, because I imagine if I have two dipoles that are aligned in a pancake, that this is going to be more repulsive versus head to tail, which is more attractive. That should have a very dramatic impact potentially on the virial coefficient value. Thanks for your time.
So, we'll go back to your answer more. So, I mean, there will always be some other piece of the generalized scattering, right? So it's not. So in that sense, its cancellation is not going to happen in the actual physical system. Right?
All right.
I mean, so have you thought about? This basically what you're saying here is if there's any short range physics that affects the short of the dipole range physics that affects the generalized scattering rate, then you will see this linear term and there's a chance to actually see the dipole effects. Did I understand this correctly?
Yeah, so in the regime that we were considering, which is basically all the short range physics is kind of subsumed in this in that hard wall. If it's possible to actually use that to represent an experimental realization of that, there is some flexibility in adjusting the virial coefficient value. I don't know if I answered your question.
So you mentioned it's hard to see the dipole effect via off resonance, but suppose you are on resonance, then how much the effect is going to be, and can you get a resonance with a reasonable width?
It's a good question. The work that we've done was always these are very narrow resonances. I mean, I had plotted the scattering lengths on the log scale, so that's actually a very small resonance width. So I guess it's still an open question whether we could actually accurately tune towards one of these resonances. But to answer your other question of if we could actually, if we could go to a more resonant value, could we actually see the dipole effect? I imagine so, but once we go to a more a resonant value, because of the coupling with the angular momentum channels, I imagine that the P-wave effect would probably be most dominant. So we might actually just see the P-wave effect when we might want to see some other effect, but it would be dominated by P-wave physics. I didn't show, but in the two identical boson system, if we actually go towards unitarity, the S-wave virial coefficient completely dominates the virial coefficient value. So
it's only over the P channel even.
Sorry, I was trying to answer your question through analogy to the S system. Yeah, so very quickly, so what I have plotted here is the S-wave, two identical bosons. And what you see is that unitarity, which I showed earlier is this value of 1/2. It completely dominates over the actual dipole effect. So if we go to a resonant L equals 1 channel, that might actually dominate the fermion system over the dipole effect. So we can't be too resonant.
So when you when you show the virial coefficient for the unequal mass fermion system, you mentioned you showed the sign change of virial coefficient as a function of the mass.
Yes.
And you mentioned that implies formation of three-body state. What kind of three-body state did you really mean?
So what I meant here is I'm actually ignoring any of the non-universal trimers that appear at mass ratios like 8.5 or so up to the FMOC trimer. So I'm ignoring all of the more interesting physics in this regime. But regardless of that fact, I still see an increase in the virial coefficient as I head towards the mass ratio of the FMOC trimer unitarity.
So if you do include, assuming that if you do include the non-universal three-body state, what do you expect for the virial coefficient?
I would expect, if we did include that physics, because we're including bound states, I imagine that the virial coefficient would become positive at other values of the mass ratio. So but that's more work that would be interesting to look into that I haven't